So hello everyone, good morning. Here I'm going to present my internship work that I did at Naver Labs, efficient compression of multitask multilingual speech models with my supervisors here present, Marcely, Vassilina, and Caroline. This project is, first the agenda for today. We're going to present the objectives, the main objectives in the beginning of the internship. Some bias analysis we did in a large speech model, a new method for compression that we propose for this large speech model, results on the validation we did of this method, this approach, and some conclusions. This project is under the GK project, which is funded by ANR and focused on identifying and mitigating bias, fairness, and ethical issues when compressing NLP models. Basically, in this new area of the large foundation models, we have these models that can get to even like 100 billion parameters, super big models that we know that they are more or less kind of fair, and because they are training with a lot of parameters again, with a lot of data, high quality and bad quality data, but that they are controlled data. But the problem with these models is that they cannot be used in several applications due to hardware constraints or time constraints, which leads a lot of people to focus on compression of this model. That can be quantization, we reduce the precision of the operations of the model, pruning techniques where we remove part of the models, or distillation where you learn a smaller model to mirror the performance of this model. And with that, you can get a compressed version that allows for the NLP products we have in our lives. But the problem here is that it's not yet clear what these compression techniques introducing this model, what type of bias or how this model will behave in specific outlier cases. So this is the focus of the project, and specifically in the internship, we want to understand the bias of large speech model whisper and how this is amplified or reduced specifically by quantization, that is one of these types of compression. With speaker-related bias like gender, age, and accent, and model-related bias like model size, resourcefulness, etc. And we want to propose a better compression approach to reduce potential disparities found. For the experiment setup on this bias analysis, we started with ASR massive multilingual datasets commonly used, FLIRs and Common Voice. These datasets have demographic information about gender, language group, accent, age, and that is useful for this type of bias evaluation. From these datasets, specific FLIRs, we create a balanced gender benchmark in which we use the sentences, and we guarantee that all sentences in the benchmark have one female and one male recorded transcription, respective transcription. And we propose a classification on the resourcefulness that is based on the amount of training data that this model, original model whisper have in a weekly supervised manner. And then we compare the performance before and after quantization use LLM Intent 8. That is the most used quantization method for NLP nowadays, NLP and transformers in general. And we focus on first an aggregate analysis for this to understand the bias, and then a sentence level analysis to understand how these biases are impacted by the quantization. So here's some results. First, we plot here the performance for the language based on whisper, ASR based on the resourcefulness, marking the resourcefulness. And we can see that the low resource languages have the worst performance on ASR, are the worst ones, even getting super bad, more than 100 word percent, or more than 100% word error rate. So it shows that the low resource languages are the ones that already have less performance in the model, as expected. Moreover, some other results show that we have speaker-related bias in the model, like gender-related bias, accent-related bias, and age. But when you look at after the quantization, we see that these speaker-related bias are kept almost unchanged. We see that only few sentences are are changes in the difference between them is super small here, male, female. In the case of gender, but we can see also this in accent and age. Basically, the speaker-related bias are not changed by the quantization. But on the other hand, the resourcefulness bias, the model-related bias, are indeed more impacted by quantization. It makes like a stair you can see here, before and after, worse and better than after quantization. And you see that it makes a stair such a way that for super high resources, almost all the sentences are kept the same, while for low resource and extreme low resource, we have more than 20% of the sentences impacted negatively. Also, in more dramatically, quantization impacts differently different sides of the models. While in the large V2 model, that is the best model, we have a bit more than 10% of the sentences impacted. For the smallest model, tiny, we have almost half of the sentence impacted by quantization, which means that this method is really impacting half of the cases here. And this is particularly dramatic because most part of the parameter efficient methods using NLP involves applying quantization first, regardless of the model size. And we've been seeing these being used in the literature, in official tutorials of frameworks, also applied in the production scenarios. This quantization being applied without bias analysis first. So overall, this bias analysis shows that Whisper presents some speaker-related bias. They are in general capped by quantization. However, model-related bias are amplified. Quantization impacts differently different sides of the models. Small models suffering more performance degradation, and low-resource languages also being the most impacted in all scenarios. And this poses a question. That is, can we improve the performance of the smaller models for languages in which the small model perform poorly, but the best model perform well? So how we can bridge this gap? And for that, we propose the Whisper architecture that aim at bridging the gap of smaller models should the best for languages that are more impacted by the course of multilinguality. The course of multilinguality is a phenomenon that is basically, if you want to, in multilingual models, you want to increase the support of the languages. In this model, we have to increase the amount of parameters. And this is particularly bad as it makes more hard to use these models in real life applications. And to solve that, we propose a knowledge distillation from the best pre-trained model to a smaller version of this pre-trained model. And we evaluate if we can mirror the robustness to these smaller models, the robustness that this good teacher had. But this poses another challenge, that is, how do we distill a model without knowing how it was trained, the training data and the learning objective? And to deal with this part specifically, we see from the literature that the course of multilinguality impacts more specifically the feed-forward network of the transformer. So we focus on that, training only this part and keeping the rest of the model free. And more than that, we switch this feed-forward network for a language-specific routing, CLSR layer, that is initialized with the previous values of the feed-forward network, which means that here it was the block of the feed-forward network. We change this for language-specific blocks and a shared multilingual block. This shared part, all these blocks are copy the values from the feed-forward network. The shared part are kept free, and the language-specific ones are trained. And we also train a language-specific gate that learn for each language when to choose this new learned model or the previous one for the scenario. And here, the novelty is that this is a parameter-efficient distillation. I forgot to mention that this is a good trade-off between mixture of experts and adapters, because adapters, you have to use the same adapters always. And for mixture of experts, you have a lot of experts and you have to run all of them in inference time. Here, you can run only the language-specific one that you are interested in. And this is novel because it's a parameter-efficient distillation, a new way to do a parameter-efficient distillation. And also, we are distilling from a pre-trained teacher to an already pre-trained student. We are not starting from scratch here. To validate this method, we train the proposed architecture with an default knowledge distillation and compare with baselines. That is LoRa only on the feed-forward network, because LoRa usually is used more in in the attention weights, and full fine-tuning. We train in a downsample common voice and evaluate on FLIRs, and use FLIRs as an out-of-domain setting to evaluate and ensure robustness. So it's the way we found to evaluate robustness is evaluating a different data set. In the FLIRs specifically is more challenging, have almost double the size of the sentences, so it's more complicated. And we select languages that have a performance gap that are bigger than 11 word rate, and that overlaps in both data sets, and that we would be able to have at least 3K, 10K, and 28K sets of utterances for fine-tuning. So with that, we get to a number of languages that make sense for the study. Training these models on 10K data sets from Common Voice. Here the results we found. Basically, our methods with CLSR with fine-tuning and with fine-tuning knowledge distillation, which better out of the main performance for most part of the language, showing that we were able to mirror this robustness, and especially on the knowledge distillation, because knowledge distillation were able to further improve this performance, reducing the whisper small out-of-domain gap in 39%. And this was done only with 10% parameter overhead, which means around 25 million parameters, which is negligible if we compare the size of small to large. After we did a study on the scalability of the method with respect of the data, fine-tuning data amount, and we could see that here we trained for Catalan, Tamil, and Thai. They were the only languages that were possible to work in all these settings, with 3K, 10K, and 28K data. And with that, we could see that our models with knowledge distillation were in general more useful than the CLSR fine-tuning alone, showing that indeed we could mirror this robustness. Also, our approaches, both approaches were always better than LoRa adapters, showing that, okay, it's even LoRa adapters have similar amount of parameters here, just 1 million difference. And also we show that with more data, we can improve even more the performance, reducing the performance gap by 28%. With an interesting phenomenon here, that is the first time with 28K that Catalan surpassed its starting point on out-of-domain performance. And this is interesting because Catalan is a high resource language, so it shows that eventually we have a relevance here on the amount of training data. And because of that, we conducted another study that is related on resourcefulness. We trained as much as we could of languages in the 3K setting and in different language families, different resourcefulness. So we could evaluate how the resourcefulness of the languages impact the performance of our method. Here is in the lower part, we have in the upper part, we have the performance in all these languages, but here we create a table where we group these languages by resourcefulness. And what is interesting here is show that for high resource languages, our method struggles to surpass the original performance, out-of-domain performance of Whisper. So which means here, for instance, Whisper Small before was better on FLIRs than after our method, while when you look at low resource, extremely low resource, we see bigger improvements, with the knowledge distillation being even the best option overall. So these, higher resources then struggle to beat the start point in our field data. We need more data. And lower resource languages benefit more from both architecture and distillation part. And we had similar results before, Catalan surpassing its starting point only with 28 data. In the 10K case, Polish and Ukrainian were the only cases where methods lose to LoRa, so were the cases where with high resource languages. And this makes sense for our objective of tackling the course of multilinguality, because low resource languages are the one most impacted by this phenomenon. So learning on the feature domain leads to performance increase for them. But the gap on high resource language is probably due to other factors, not to the course of multilinguality specifically, requiring to optimize the other parameters in the network, and also increasing the amount of training data, especially if you want to keep training this part to be able to make up for the whole model. To conclude then, in this work, we show that Whisper presents both speaker-related and model-related bias. Model-related bias were amplified by quantization, with low resource languages and smaller models being more impacted. We introduced Whisper, that is a parameter-efficient distillation that uses language-specific gated models. And this approach consistently surpasses other adaptation methods and effectively reduce the performance gap for a small model. And as a future work directions, we can point out that it would be interesting to further the bias investigation we did to 4-bit quantization and to other model families to understand if this is a pattern that happens in your models, and then call out for a more attention on these aspects. And also investigate the impact of our approach, Digital Whisper, on speech translation, especially how this affects translation to English, and also see if the use of these models also arise some zero-shot, many-to-many translation capability. That's it. Thank you very much.
Thank you. So, so how should we proceed now? I have a couple of questions to ask you, clarification questions mostly.
Yes.
Okay, so maybe we can start with that. Yeah, I mean, so you have this curve showing the performance as a function of with the color code being the resourcefulness of the languages. And I was wondering, because you have some obviously the worst performance are blue, but you have some blue in that are also quite good. No, there's at least one point which is below 20%. So that means that you can have very good performance with very, very low resource languages. I was wondering what do you think of that? What language is that, and do you think what could explain this?
Okay, this one that you mentioned specifically, this blue point, is Galician. You cannot see it because it cuts the even languages, like the odd end languages, but it's Galician. And Galician was trained on 9 hours only, which is pretty impressive, this performance, so only 9 hours of weekly supervised data. But the fact is that Galician specifically benefits a lot from super high resource languages, mainly Spanish and Portuguese. They are super similar. Even some languages consider Portuguese and Galician the same language, or dialects of the same language. So with that, the case of the Galician specifically was that we had similar super high resource, close related language that they benefit from probably. Other cases here, also these ones in orange, also are related to languages that have similar phonetics or similar something similar to high resource languages that had a good amount of training data. But if you look at the ones that have less training data, this represented less on the in proportion to the amount of training data. Then these ones were, and they don't have any relation. Then these ones are the ones that are here, super bad. But there are cases in the contrary. For instance, Afrikaans is a language that's super similar to Dutch, to German, but they also have a super bad performance. They are around here. So yeah, but we see that some languages can profit from these similarities.
Yeah, I mean, yeah. Do you think it could also be like channel factors, microphone recording conditions, and stuff like that that could especially for if you don't have a lot of data that will modulate.
Yes, indeed. Yeah, and also, yeah, we know that Whisper was trained on data from YouTube mainly, so we know that the conditions of can vary a lot if it's indoor, outdoor, yeah. And some languages that have only 5 hours of training, we don't know which proportion of this was really good quality data.
So I have another question on the figure 10 on your manuscript, where you show the degradation or improvement of performance for quantization.
This is not here.
Yeah, this one. Yeah.
This one.
So well, I mean, so I found, I mean, the way in which you describe this figure is to say that extremely low resource languages are more impacted, but in fact they are impacted. Sometimes they go better, right? So basically, sometimes it's worse, sometimes it's better. That's what the so the thing is that with this representation, it's actually not easy to see exactly how the performance is, right?
Yeah. We wanted also to understand if we can draw some line on when it's gonna get better and when it's gonna get worse. We tried several things, for instance, crossing these with gender, with accent and this stuff, even with some metrics of evaluation, and we could find it. So what we can conclude so far, of course, we could investigate more, but it's not clear why some cases got better, some cases got worse. So we can assume that it's random, and then it's concerning, because if you don't know if it's gonna get worse or better, you should not apply it in this case, right? If we knew that okay, in this case it's gonna get better, we knew that, but here we tested and did several things, but we couldn't find.
Okay, so you are worried about the variance, not so much the effect on the performance. So each of these bars, they contain what? They contain languages, right? Or they contain utterances. What is your granularity of analysis here?
Yeah, it's utterances, and the amount of utterances in each is kind of similar, because although we have less sentences of extremely low resource, we have more languages in this category, so it's kind of similar, the amount that each one has. And yeah, here is the amount of sentences they are impacted, or get worse, got similar, got better.
Okay. Yeah, I think it will still be interesting to have just the raw performance before and after quantization. You know, you have your graph with all the languages like this. You could just have another line with just to see how whether it degrades really a lot, or it's just like this. It's adding like noise, like this graph is showing. Okay, so. Yeah, I guess in your manuscript you also have you mentioned some analysis of the gating weights. But you didn't have time to the gating activation. You didn't have time to talk about it, so I wonder whether you have some comments on that.
Oh yeah. It was on a slide, but because of the time we couldn't do it. But yeah, I discussed here what we can conclude from this. Basically, we had here the amount of trained data and the amount of activations for these 3 languages that we had in all sections, Catalan, Thai, and Tamil. And what we found interesting here is that if you have more data, or if you have a better teacher, the more quality you have of the data and of the teacher, more reliable will be the language-specific path. And this is showed especially in Catalan. There is a super good example because the data is really good. The teacher have already an impressive performance for this case. And it's interesting on the contrary. For instance, in Thai, we could see that the data set is not that good because knowledge distillation actually bring a better, more reliable model than the fine tuning. So probably it's because the teacher corrects the wrong transcriptions in some cases of the data set. So yeah, overall we could see that knowledge distillation leads to a better, more reliable modules, and that the better is the teacher and the better the data, the better will be the method. With better, I mean not only with specific performance, but mainly out-of-domain generalization. Yeah.
Okay. Yeah, I guess I will have other questions, but we're going to run out of time. How should we proceed? I mean, do you have other member of the jury have questions as well, or you want to proceed? Yeah. How do you want to?
If you have no more questions, I think it's fine for us, because since we know the work, I don't think we need to ask anything. So feel free to ask your question.
Yeah, I guess so. Regarding the evaluation, so I received the document that you where you put your own appreciation. Now, yeah, we need to put a grade. So I think maybe what we could do is like have a small discussion, just the jury members, to discuss that, and then yeah, that's it, right? No, I've never done that, so it's just like for me a bit the procedure is a bit obscure to me. So
okay, yeah. Okay. So Thomas, you can leave the room.
Yeah.
I will ask Johan and Vivek if you can quit the Zoom.
Okay.
Yes.
You don't need Thomas anymore. Or shall we ask him to come back and?
No, I think you can. Yeah, you can. I mean, obviously he's around, so you can talk to him.
We can send him a message that he comes back.